Welcome back to CMOS radio frequency integrated circuits. We are in the middle of the 11th module. We have been discussing frequency synthesis, and part of frequencies, as part of frequency synthesis, we were first discussing the phase locked loop. So, in this lecture I am going to introduce to you the charge pump and move on and build a phase locked loop. But before that, a brief recap of what all we have done. We have understood that these are our basic building blocks. First of all, we have understood the characteristics of the input. Phi ref, it is really a phase, the phase of a voltage. So, phi ref needs to be tracked. The phase of this voltage, the voltage is coming from a crystal oscillator. The phase is a ramp. You want phi out to be tracking this ramp. So, to do that you have to make a velocity control system. That is number 1. Number 2, the phase detector is something very special. It is not a simple subtraction. The inputs to the phase detector are really the voltages corresponding to phi ref and phi out. You have to design a circuit whose output is the difference of the phases of these two voltages. Okay. The third thing is the voltage controlled oscillator. The voltage controlled oscillator, that is the plant for the control system, has characteristics of k by s, something of that nature, k by s. All right. So, here we assumed that I have got a linear VCO. This assumption need not be true. Our analysis will work in spite of this assumption. So, without any loss of generality, k could be negative, for example, the value k over here could be negative. Without any loss of generality, it could be offset from 0, and that brings us to, I could easily create a curve that looks like this. So, without any loss of generality, this kind of a structure is going to work for us. All right. Next, what we did in the previous lecture was we tried to build the first building block out here, the phase detector. Now, this phase detector, we figured out that the input signals are really digital signals. So, there is no reason why the phase detector should not be a digital circuit. Our first experiment was with an XOR gate. We found out that the XOR gate kind of works, but it works at a bias point of pi by 2 or minus pi by 2, as the case may be. Right. So, this was our first attempt. The next attempt was a more organized one, and here we first made a state machine diagram, state diagram. It was a funny kind of state diagram with which responded to the edges of the two inputs, and then after that I constructed the machine corresponding to that particular state diagram. So, it is easy to understand this machine as well. Now, the outputs of this machine are +1 or -1. +1 corresponds to the symbol +1, -1 corresponds to the symbol -1, and when both of them are 0, the net result is 0. If both of them happen to be 1, which should not be the case, because as soon as both of these outputs are equal to 1, clear will be activated and both of them will be cleared. Right. So, this is our phase detector. So, the output is a digital representation of the sign of the phase, whether it is a positive or a negative, or whether the phases are identically equal. The duration of this pulse indicates how much the phase is off by. So, if my reference voltage is like this, it is not really phi ref, it is V ref, and V out is, let us say, 90 degrees behind V ref. In that case, the output of my PD phase detector, that is my PD, the output of the PD, there are two outputs of the PD. There is a +1 output, there is a -1 output, right. Now, the way the +1 works is when the edge of the reference clock comes, immediately it goes to +1, and then it waits for the edge of the V out, then it goes back to 0. All right. And when the is, what about the -1 output? The -1 output is always 0. Okay. So, if my phase difference phi ref minus phi out is 90 degrees, 90 degrees is pi by 2, then the PD output is +1 for 1/4 of the time, which means that the PD output, the average PD output is VDD by 4. Okay. If I had phi out leading phi ref, then it would be -1 1/4 of the time. So, the PD output would be minus VDD by 4. Fine. So, the gain of the PD so, for pi by 2 phase, my output is VDD by 4. Therefore, the gain is VDD by 2 pi. All right. So, this is what I have got as the gain of the phase detector. So, the model for the phase detector is something that looks like this. Okay. But we are not done as yet. The next thing you have to understand is that the output of the phase detector is a digital code, right. It could be 1 0, which means the output is +1. It could be a 0 1, which means the output is -1. It could be a 0 0, which means the output is 0, and it will also be 1 1 for a very short duration. If you notice over here, for a very short duration, both the outputs are 1. As soon as both the outputs are 1, the AND gate output becomes equal to 1, and the clear is activated. So, this delay, the delay of the AND gate and the delay of the clear operation taking effect, that total delay, for that duration 1 1 will also be true, okay? And 1 1 really means a 0 as far as we are concerned, and plus 1 minus 1 it is equal to 0, right. So, what we have got to do over here is some kind of a digital to analog conversion. It's a crude digital to analog conversion that we need to do. We also have to do some sort of averaging in the process. Okay. So, the correct output of the phase detector is the average value of the plus 1 signal minus the average value of the minus 1 signal. That is the correct output of the phase detector over a given period, right. So, over a given period, I want to add. So, plus 1 over here corresponds, okay. Let us, instead of plus 1 and minus 1, let us call them up and down, okay. It's a, this is going to be the nomenclature. So, up corresponds to a plus 1, down corresponds to a minus 1. Now, what we have got to do is we have got to convert this up and the down signal into an analog value. Why do we have to convert it to an analog value? Because we need to use the output of this phase detector to eventually drive the voltage controlled oscillator, which is an analog. This is an analog signal. Right. So, how do you do digital to analog conversion? Fast digital to analog conversion, you can do something like current steering. Yeah. So, this is a typical current steering DAC. Very typical current steering DAC, or actually you need not even waste that current, you can push it to another resistor and you will get a differential output, fine. So, this is a fast current steering DAC, we can use something like this, right, and the output is an analog version of the sine of the phase difference between phi out and phi ref and phi out. Agreed? Now, what I am not showing over here, I have not yet done over here, is the fact that I am not interested in the instantaneous value of up minus down. I am interested in the average over a period of up minus down. So, over one period, what is up minus down? So, instead of the resistor over there, the easiest fix is to put a capacitor. So, as long as up is high, the capacitor charges, and when down is high, the capacitor discharges. You get up minus down. If up and down are high at the same time, then the current just passes through, does not charge the capacitor at all or discharge the capacitor, right. So, this is the basic charge pump. Now, there are a lot of problems over here, we will come to them one by one, but the understanding is clear, right. What I have got is unfortunately the integral of the instantaneous up So, consider up and down as either plus 1 or minus 1, plus 1, 1 or 0, right. So, this is what I have got. Okay. It is not the average at all. 1 by this, 1 by the total time during which I have done this job is going to be the average value. This is not the average value. Is it the average value? No. So, this is what I have got at the output of the charge pump. Now, if the phase difference between phi ref and phi out is 90 degrees, just like before, then up minus down will be 1 for 1/4 of the time, right. So, that means that this result is going to be I naught by C, 1/4 of that integral minus infinity to the current time. Is this all right? Is this all right with everyone? So, what I have got essentially is this. I have got phi ref and I have got phi out, and I have made a digital circuit. I have got two signals up and down, and with these two signals I am trying to figure out whether I should charge a capacitor or discharge a capacitor with a certain amount of current. Right. So, this entire block can be modeled, this entire block can be modeled as so, if the phase difference is pi by 2, then it is 1/4 I naught by C. If the phase difference is 1 radian, it is 1 by 2 pi times I naught by C. So, this is the model for the entire thing. Okay. It is an approximate model. It works only when the time for which you integrate is much larger than the size of the period. Right. That is the only. So, here this t has got to be much larger, many periods have to be covered, right. Then only the average can be taken out of the integral. Otherwise, this is what you have got to do. This is the truth. This is an approximation that works only when the size of the integral, the time duration over which you are doing the integral, is much larger than the period, or rather than the the period of each clock cycle. All right. So, this is the model that we have. Now, if we plug this thing into our system, if we plug it in to our system as is without any further modification, then unfortunately our system is going to oscillate, because there are just two integrators with some gain. Okay. Do you agree or not agree? You have got 1 by s squared in the denominator of the loop gain. So, if you have 1 by s squared in the denominator of the loop gain and it is negative in sign, then in the overall denominator you are going to have 1 plus some constant times s squared, which means you are going to get poles on the j omega axis and the system is going to oscillate, it is never going to stabilize, right. We want to make a stable system. So, this is not going to finally do it, just this is not enough. So, if I just make a charge pump and connect the output of this to my VCO, it is not going to work. Why not? Because I have got two integrators and as a result my system is unstable. Okay. So, what do we do? Now, if you have done your job, that is, your job was to go back, open your control theory book and read about velocity control, how it is done. There are several techniques. One of the techniques which is quite popular is to add a 0 into the system. So, the point is that I do not want to just put two integrators over there. What if I had my current, let us say this is this is my average current. What if instead of pumping it into a capacitor, I pumped it into a resistor, capacitor and capacitor. Let us call this C1, let us call this C2 and let us call this R, or let us say this is C and this is Cx. Okay. So, this is the model for the current coming out of the phase detector or the DAC, the current steering DAC, that is the current coming out of the current steering DAC on an average, that is what it is. And let me push that current into this kind of a system and we will take this output to the VCO. So, first of all, what is this impedance that I have created? R in series with C, in shunt with Cx. What does this look like? So, R plus 1 by SC, this whole thing is in shunt with Cx. So, this is the impedance. Okay, I have neatly divided it up into poles and zeros for you. The impedance has a pole at 0, it has got a 0 at minus 1 by R c, and it has got another pole at minus 1 by R times C series with C x. Okay. So, C in series with C x is smaller, it is a smaller value than either of C and C x, it is definitely smaller than C. So, you have got a pole at 0 at the origin, then you have got a 0 at minus 1 by R c, and then you have got a pole at minus 1 by R c in series with C x. Right. So, this is what I have got as my loop filter. So, this is called the loop filter, and if you now do your analysis, so instead of 1 by 2 pi, I am going to write it as I 0 by 2 pi. Then pole at the origin, one more pole and one more 0, and this entire thing is going to control my plant. My plant is some constant divided by S, that is generating phi out, phi out. Now, if you do your analysis, first of all let us check for stability, it is going to be stable, but let us see, let us just work it out. So, the open loop gain is I naught by 2 pi times 1 by, or rather k, I am going to call it k, not k VCO, times S squared C plus C x times 1 plus S C R by 1 plus, let us call this C in parallel, C in series with C x, let us call it something else, let us call it C s, or let us call it C 1. Okay. C 1 is much smaller than C, that is the only thing over here. So, this is my open loop gain and so this is your final expression. Now, of course, this will require simplification. It is very difficult to handle these numbers. So, I naught times k times 1 plus SCR, that is what I would like to keep in the numerator, and in the denominator I am going to keep I naught times k times 1 plus SCR plus 2 pi times S squared C plus Cx times 1 plus S C1 R. Okay. And further you would like to divide numerator and denominator by I naught times k, in which case this is what you are going to end up with. Little more simplification will actually it is pretty neat. It is not bad at all, it is quite neat in fact. Okay. So, this is your system, your closed loop transfer function. Still not clear if the system is stable at all or not, right. And to prove stability, what you need to do is some sort of an estimation of where exactly the poles are. You could do that, or you could start with this polynomial, this expression, and do a Routh-Hurwitz criterion. Remember Routh-Hurwitz criterion? Yeah, you work with the open loop gain, and you see whether when you put the open loop transfer function in a closed loop, your system is going to be stable or not. That is the Routh-Hurwitz criterion. So, you could do that as well, or you could work with this final polynomial and find out where the roots of the denominator are, whether they are on the right half plane or on the left half plane. Now, what you have to do over here is you have to understand that C1 is small, it is smaller than Cx and C, and C plus Cx is of course larger than C and Cx. If I say that let Cx is, let us say C by 10, if I choose Cx to be something like C by 10, then C plus Cx is going to be approximately equal to C, and C1 is going to be approximately equal to Cx. right. C x is much smaller than C. All right, and you can show that under such conditions this kind of a system is going to be stable. There is not going to be too much of a problem with this. Look, you just have to find out where the roots are, and you have a few knobs. Your knobs are C, C x and R, and you have to make sure that C, C x and R are such that the roots of this polynomial lie on the left half plane. You are done. So, that is all there is to this. Okay. So, that is the PLL architecture. I am going to make a phase detector using my beautiful digital circuit. The phase detector takes its input as 2 voltages, but for yeah sure. It is going to generate up or down. Now, up or down also has significance. Up means that the Vref is running fast, Vref is running fast, I need to increase, I need to make the plant run faster. So, I need to speed up the plant. Down means that V out is running too fast, I need to slow down, right. That is why the terminology is also up and down. In the books you will see up and down, not +1 and -1. But really these two signals are digital codes for +1 and -1, together they make a digital code, right. And then we have got the charge pump. The simple charge pump is no good. We have to make a more sophisticated loop filter than a simple capacitor. Typically, C is going to be much larger than C x. C x is about a tenth. The thumb rule is keep C x about a tenth or a fifth of C. R and C together will determine the loop bandwidth. So, this filter, this is a filter, this filter has a bandwidth. Look at our expression. This filter has a bandwidth, it has a pole at DC, it has a pole at 0, okay, and that pole is given by C plus C x, 1 by S C plus C x, right, the total capacitance. In conjunction with R, it is going to define the bandwidth of my loop. So, where was I? So, if I plot the response for this kind of a system, I am going to get infinite gain at DC, right, and then I am going to get a 0 at minus 1 by R c. What does that mean as far as we are concerned? So, if I do the Bode plot, it is falling at 20 dB per decade, then it is going to level off at minus 1 by R c, and then again it is going to start falling off at minus 1 by R c 1. So, this is called the loop bandwidth. Why? Because at that frequency I will get 3 dB less than this value. As the impedance. So, that is my loop bandwidth. Right. So, that is the all important loop bandwidth. Now, this loop bandwidth, what should its value be? Can the loop bandwidth be as high as the oscillation frequency? If the loop bandwidth is as high as the oscillation frequency, then it is like this: Vref and Vout are changing at the oscillation frequency. Those changes will go right through this entire loop. Okay. Think of this entire thing as a filter. Vref and Vout are changing at the oscillation frequency. Do you want this particular node to be changing? No, this particular node is going to the voltage controlled oscillator. This is the control voltage. It should be a fixed voltage, because if this voltage is changing, then the frequency of the VCO will also be changing. You do not want that, you do not want this voltage to be changing at all. Right. So, the idea is that this loop bandwidth has got to be much lesser than the oscillation frequency by itself. How much lesser? It turns out that if it is not at least 10 times lesser, then the system is not going to have the dynamics that we described here. In fact, what is going to happen is that this approximation that we made is no longer going to be valid. We made an approximation over here. The fact that the output of the loop filter is a time average, that approximation is no longer going to be a valid approximation if the loop bandwidth is larger than something like a tenth of the frequency of oscillation. If the loop bandwidth is as large as tenth of a frequency of oscillation, then that means that minus 20 dB is the rejection at the frequency of oscillation, which means that if your whatever is the amplitude of oscillation, 1/10 of that is going to come right through. Okay. It is a heuristic argument. Unfortunately, this cannot be confirmed in theory. You need to read a couple of papers. There are some excellent references which I shall give in the notes for this particular lecture. There are some excellent references. You can study the references, and this particular claim, the 1/10 number, where it comes from, it is really more of a thumb rule. It works. If you go beyond this, if you make loops that have larger bandwidth, loop filters that have larger bandwidth, then unfortunately this approximation that we made over here is no longer valid. Once the approximation made is no longer valid, then you have to work out the dynamics of this phased lock loop with greater thought, with greater basically the problem is at some point you have to do a conversion between discrete time and continuous time systems, right, and the complexities of that are going to be much greater. So, it is going to go beyond classroom teaching. So, this approximation works when the loop bandwidth is less than a tenth of the oscillation frequency. All right. Now, why would you want the loop to have large bandwidth? Why? Why do you want the loop to have large bandwidth? Is there any reason? Is it okay to have 1/100th the loop bandwidth to be 1/100th of the oscillation frequency? Does it matter? It does not matter if the VCO is good, but remember this VCO that you are making, one of the reasons why you are making the voltage controlled oscillator is, I am sorry, one of the reasons why you are making this phase lock loop is to track the phase of the reference. You know that the reference is coming from a crystal oscillator. This crystal oscillator has far superior phase noise performance than the oscillator that you have built on chip, right. That is the reason why you are making this phase lock loop. Okay. So, you want to track the reference phase. Now, if you make a large bandwidth for your tracking, then over a large bandwidth the output of your oscillator will look like the output of the crystal, the reference. So, suppose this is the spectrum of Vref, and suppose if you just run your VCO as is, then this is your spectrum. I am sorry, it is probably not as bad as this. Let us say this is what it is. I have exaggerated a lot over here, and now suppose your loop bandwidth is this much, then that means that the output, the final output V out will have characteristics that look like the reference within that loop bandwidth, and beyond that loop bandwidth it will look like a free running VCO. So, within the loop bandwidth it is going to look like this, the final output. Outside the loop bandwidth it is going to look like your free running VCO, which has horrible phase noise. Okay. So, that is the reason why you want this loop bandwidth to be large. You want this loop bandwidth to be as large as possible because of this. On the other hand, the loop bandwidth can't be, it can't increase forever. The loop bandwidth can be at most something like a tenth of the oscillator frequency. Now, that means that when you build your phase lock loop, you would like its loop bandwidth to be exactly equal to 10th of the oscillation frequency, because otherwise you lose in terms of performance, right. So, with this understanding we are going to proceed in the next class. So, we have kind of tried to build a phase lock loop. I do not exactly know if you completely understand what is going on over here or not, but we are going to see more of this in the following classes. Okay, thank you.